integral that secretly draws in the complex plane, the integral from 0 to 1 of x to the ix dx. First trick, rewrite it. X to the ix equals e to the I times x times natural log of x. So the magnitude is 1. It never grows or shrinks. That means every x gives a point on the unit circle with angle theta equals x times natural log of x. Now watch x slide from near 0 to 1. The point walks along the circle, and each tiny vector contributes. Add up all those directions, and the real integral becomes a complex number, approximately 0.9633 minus 0.2461i. Let us explore why. The transformation strategy is simple. Turn x to the ix into something we can expand. Start with a general identity, a equals e to the natural log of a. Now apply it to the function. X to the ix becomes e to the natural log of x to the ix. Next, use the log rule. Natural log of a to the b equals b times natural log of a, so the exponent drops down cleanly, giving e to the ix times natural log of x. This is the key move. Because exponentials have a built-in series, e to the u equals 1 plus u squared over 2 factorial and so on. Let u be ix natural log of x. Substitute it directly into the series. Now, the function becomes 1 plus ix natural log of x plus the square term plus more. Finally, compress it with sigma notation. E to the ix natural log of x equals the sum from n equals 0 to infinity of ix natural log of x to the n over n factorial. Now the integral has a series engine behind it. Integrating the series is where this problem stops looking mysterious and starts looking structured. Start with the identity, x to the ix equals e to the I times x times natural log of x. Now expand the exponential as a power series. E to the ix ln x becomes 1 plus ix ln x plus the quantity x ln x squared over 2 factorial plus more terms. Here is the payoff. The integral from 0 to 1 of x to the ix dx becomes an integral of a sum. And that means term-by-term integration, the integral of 1 plus the integral of ix ln x plus the integral of the next term, and so on. Now compress it into sigma notation. The integral from 0 to 1 of x to the ix dx equals the sum from n equals 0 to infinity of the integral from 0 to 1 of ix ln x to the n divided by n factorial dx. Next, separate the constants from the x part. I to the n over n factorial does not depend on x, so it comes outside. So the whole expression becomes the sum from n equals 0 to infinity of I to the n over n factorial times the integral from 0 to 1 of x to the n times natural log of x to the n dx. To keep it clean, define that integral as a single symbol. Let in equal the integral from 0 to 1 of x to the n times ln x to the n dx. Then the final form is simple. The integral equals the sum of I to the n over n factorial times in. Next, solve for in. Start with a helper integral that is easy to solve. The integral from 0 to 1 of x to the a dx equals 1 over a plus 1. Now comes Feynman's trick. Differentiate both sides with respect to a. On the left, the derivative moves inside the integral. The derivative of x to the a is x to the a times natural log of x. So the left side becomes the integral from 0 to 1 of x to the a times ln x dx. On the right, differentiate 1 over a plus 1. That gives negative 1 over a plus 1 squared. So we have a new identity. The integral from 0 to 1 of x to the a times ln x dx equals negative 1 over a plus 1 squared. Differentiate again, and a pattern appears. Each derivative adds one more power of ln x and pulls down a factorial. In general, the integral from 0 to 1 of x to the a times ln x to the n dx equals negative 1 to the n times n factorial over a plus 1 to the n plus 1. Now set a equal to n, and that gives in exactly. We are ready for the clean payoff. Recall the structure. The integral from 0 to 1 of x to the ix dx equals the sum from n equals 0 to infinity of I to the n over n factorial times in. Now plug in the closed form, in equals -1 to the n times n factorial, divided by n plus 1 to the n plus 1. Substitute that into the series, and here is the satisfying moment. The n factorial cancels perfectly. So the whole integral collapses to a much simpler sum. The sum from n equals 0 to infinity of I to the n times -1 to the n over n plus 1 to the n plus 1. Combine the powers, I to the n times -1 to the n becomes -I to the n. So the final compact result is the sum from n equals 0 to infinity of -I to the n divided by n plus 1 to the n plus 1. And the first few terms look like 1 minus I over 4 minus 1 over 27 plus I over 256, and it keeps going. Numerically, this series converges insanely fast. We write the result as S equals the sum from n equals 0 to infinity of -I to the n over n plus 1 to the n plus 1. Now watch the partial sums Sn. At n equals 0, it is exactly 1. At n equals 1, it adds minus I over 4. By n equals 3, the terms are already tiny, and the next term shrinks like 1 over n plus 2 to the n plus 2. So after only a few rows, the value stabilizes to a clean complex number, with a real part near 1 and a small negative imaginary part. Thanks for watching.